So this is Unit 3, Lesson 1, what is a rational number? So in this unit, or in this lesson, we're going to be able to identify what a rational number is. We're going to compare and order rational numbers, and then we're going to identify a rational number in between two given rational numbers. So I'm going to probably break this unit or this lesson up into a couple videos. I'm going to see how it goes for time. So this picture shows all the different number systems in our that we use today. So I'm going to go through the definitions of natural numbers and I'll refer back to the picture. So natural numbers are the counting numbers. So we naturally start counting with the number 1 and then 2 and then 3 and 4 and dot 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 5, 6, 7, 8, 9. Then we needed a number that represented nothing. So we thought we got all of them. So the whole numbers are the counting numbers, and then we're going to add in the 0. So there's 0, 1, 2, 3, 4, and then continuing on. And then negative numbers became of interest to us. So integers came in, and integers are both the positive and negative numbers. So we're talking dot 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 dot, -3, -2, -1, 0, 1, 2, 3, and we're going to continue on. Okay. So one thing I forgot to say is that natural numbers has the symbol of a capital N, whole numbers has a symbol of a capital W, and integers has a symbol of capital I. There have to be capitals so that we don't confuse them with variables. So, sorry, let me go back to my diagram. So the natural numbers is a system of numbers that are within the whole numbers. So notice that 1, 2, 3, 4, 5, 6. They're also part of the whole numbers, but zero's not a natural number. It's only in the whole numbers. And then the whole numbers are within the integers. So all of these integers are actually within a different number system, which is called the rational numbers. So the formal definition that you're going to have is a rational number is a number in the form of a fraction, so a over b, where a and b have to be integers and b cannot equal to 0. So rational numbers can be written as a fraction. Oops. Okay. Or we know that fractions can be converted to decimals, and there's only certain types of decimals that they can be converted to. Either a fraction can be written as a decimal or be converted into a decimal that terminates or repeats. There's nothing in between. Okay? So either when we take any fraction in the world, when we do the division, when we convert it from fraction form to decimal form, that decimal either will terminate or it will repeat. So some examples of rational numbers, I'll just change to a pen, 2 over 3, -1 and 1/4 are some, both positive and negatives. We can have -0.5. Sorry, I'm a little slow with this pen. We can have 2.3 repeating. Okay, so all of these are different types of rational numbers. Irrational numbers cannot be written as a fraction. Okay, so they cannot be written as a fraction. And decimals of irrational numbers don't terminate and they don't repeat. So they don't terminate and they don't repeat. So these are the ones that we talked about in Unit 1. Remember, the irrational numbers, they're consistently going, like women, sorry, consistently going, consistently talking, and they don't repeat what they say. So some irrational numbers, example of irrational numbers, the most common one that we know, or the most popular one, is pi. But irrational numbers are only formed of the square root of non-perfect square roots. So the square root of 23, the square root of 5, I can put a negative in front of it. That still gives me an irrational number because it's just going to give me a negative decimal. So those are all examples of irrational numbers. So in the class example, do the following numbers belong to the rational number system? Explain why or why not. So the first one is yes. Let me just change it to 10. Yes, because it is a fraction. The second one is yes, because the decimal terminates. And the second one is no, it's not a rational number because 12 is not a perfect square. Okay, so when I find the decimal of square root of 12, it is going to give me a decimal that doesn't repeat and it doesn't terminate. So we have a quick check here. It says circle whether the number is rational or irrational. Explain why it is a rational number or why it's not a rational number. So the first one is irrational, and it is a fraction because it's in fraction form. All fractions are rational. This one was supposed to be square root of 19. So let's just change that. So it's irrational, and the reason why is because 19 is not a perfect square, or when I convert to a decimal, the decimal does not repeat or terminate. Okay. This one's a rational number because it can be written as a fraction. This one, the square root of 9 is 3, so therefore it's a rational number. So you can put 9 is a perfect square. Second one, or square root of 75, is irrational. And again, two different answers. 75 is not a perfect square, or the decimal does not terminate nor repeats. Pi is an irrational number, and the only explanation that I will accept is that the decimal does not terminate nor repeats. Okay? So this is an example of a provincial achievement question that happened, I don't know, a couple of years ago. So if x is equal to 90, then which of the following expressions is a rational expression? So the answer is A. 1 divided by 90 is a fraction form. You can put the square root of 90. 90 is not a perfect square, so therefore it's irrational. And if I take an irrational number and I times it by 90, I'm still going to get an irrational number. Okay? So class notes, converting decimals to fractions. Since all rational numbers can be written in fractional form, here are some common rational numbers. So numbers that have one decimal place. So numbers that have one decimal place, if I want to write this decimal as a fraction, so one decimal place, decimal 3, I put those over 10. 0.5. Sorry, that's 0.5. So as you probably have guessed already, it's 5 over 10. And the answer needs to be reduced to 1/2. Okay, so two decimal places. So say I have 0.31. Those decimals get put over 100 because I have two decimal places. Or my last digit ends, whoops, that's supposed to be a 1. My apologies. Let me just get an eraser and erase a little bit here. or my last digit ends in the hundredths place. So 0.02, I have 2 digits. The last digit ends in the hundredths, so it's 2 over 100. And as I reduce this one, it would be, 1 out of 50. Okay. So as you guess it using the pattern, 3 decimal places that terminates would be over, 1,000. So 321. And you can check these. You can just go 321 divided by 1,000 and you're going to get that decimal. Now numbers with one repeating decimal. So now we're talking about decimals that repeat. So let's talk about 0.22222. The way that we represent that the 2 repeats is by putting a bar over top of the 2, which is called a vinculum. And since only one digit repeats, we put it over 9. So it would be 2 over 9. And again, you can check using your calculator. 2 digits that are repeating. So I have for some odd reason 3 in my head today. So let's put 34, and we have 2 decimals that repeat. So 0.34, 34, 34, 34, 34, and it continues on and on. Since 2 digits are repeating, we're going to put them over 2 nines, so 99. And as you guess using the pattern, if 3 digits are repeating, so say 213, and it's 213, 213, 213, 213, 3 digits are repeating in your decimal, so we're going to put it over 999. Now none of these can be reduced, but if they did, or if you could reduce them, then you should. So when we're converting fractions to decimals, 3 over 5 means 3 divided by 5. And you're going to get 0.6. So just a little review of converting fractions to decimals. Some people have problems with what to do with a mixed fraction. You can change it to improper by multiplying and then adding. So 3 times 5 is 15, plus 2 is 17, and then you should divide. So now you have 17 divided by 5. And you get 3.4. Okay? Most of your fractions in high school are going to be improper, so get just used to converting all your mixed fractions to improper and doing your division. Okay, so drawing a rational number on a number line. We can use a number line to compare rational numbers. So my grade 9s last year had some problems with putting rational numbers on number lines, so I just want to make sure that I go through them very carefully with you guys. So positive numbers are to the right of 0, and negative numbers are to the left. Okay? So if I want to plot this on a number line, 1 3/5, the 1 tells us where to start on the number line. So the big number 1 tells me I'm going to start at 1. And then I want to go 3/5 from 1, in the positive direction. So 5 tells us how to divide the distance of each segment. And what I mean by each segment is the segment between 0 and 1, the segment between 1 and 2, the segment between 3 and 4. I want it divided into 5 equal spots. If it was 7 on the denominator, then you would put 7 equal spots. Okay? So let's do that right now. It tells me to start at 1. I need 5 equal spots, so in order to do that, I need 4 lines. 1, 2, 3, 4. So 4 line gives me 1, 2, 3, 4, 5 equal spots. And the 3 tells me where to put my dot. Okay, so what I'm going to do is I'm just going to change the color. So I'm going to go 1, I'm going to start at 1, and I'm going to go 3 out of the 5 distances, and I'm going to put a dot there. And I'm going to label my dot as 1 3/5. And I'm sorry, this is so awkward to do this without my mouse today. Okay. So we did a few examples. 5/7. Since I don't have a whole number, I'm going to start at 0. 7 tells me that I'm going to divide 0 to 1 into 7 equal spots. That means I need 6 lines. So I'm going to try my best. 1, 2, 3, 4, 5, and 6. When I create 6 lines, I have 7 equal spots, or 7 equal distances. 1, 2, 3, 4, 5, 6, 7. And the top number says I start at 0 and I go 5 of them. 1, 2, 3, 4, and 5. I'm going to put a dot there and I'm going to label my point as 5/7. 3 2/5. I start at 3. It's a positive number, so from 3 I'm going to still go to the right. 5 tells me I divide them into 5 equal spots. So 4 lines, 1, 2, 3, 4, gives me 5 equal distances, and I'm going 2. And then I label my point, 3 2/5. Now the negative is a little bit different. The negative tells me I start at -2, so let's put a -2 here, -1, -3, and -4. This tells me I'm going to divide it into 3. So from -2, I start at -2 and I still have to go more negative. So I have to go left from -2. When I'm on the right side of 0, I'm still going to go more right. If I'm on the left side of 0, I'm going to still go more left. So I have to divide it into 3 equal spots. That means I have 2 lines. So from -2, I'm going to go 2/3 more. Put a dot there, and I'm going to label my point. -2 2/3. So class notes, compare and order rational numbers. For every positive fraction, there is a corresponding negative fraction. So -3/4 and +3/4 are called opposite because they're the same distance from 0. -3/4 and +3/4. So when you have that, you actually have opposite. They're called opposites. So it's like any fraction, we also can have decimals as opposites as well. So 0.25 and -0.25, since they're equal distance from 0, they're called opposite numbers. There are 2 strategies for comparing and ordering rational numbers. First of all is placing them on a number line. And the second one is converting all the rational numbers to decimals and comparing the decimals. So in class, I made a little point that when you put numbers on a number line, if they're in fractional form, we might need to use equivalent fractions to do so. Okay, so I just put a little note there just to remind students that we might need to use equivalent fractions in order to place numbers on a number line. Excuse me. So if I want to use the class example, if I want to do this class example, it says use the symbols of those to make the statement below true and use a number line. In this case, what I would do is I would actually convert the fraction into a decimal. So when I do my division, I'm going to get -2.5 and -2.8. So I know I'm going to start at -2. And I'm going to be going more left. I'm talking about tenths here. Since my decimal is in tenths. So I'm actually going to divide my segment into 10. So that means Okay, so there's 2.5, 2.1, 2.2, 2.3, 2.4, 2.5, 2.6, 2.7, 2.8, and sorry, I have to squeeze one more in, 2.9, and then 3. So when we're having decimals in the tenths, we divide each section into 10. I'm just going to change my color. Negative 2.5, I start at negative 2, and then I go another half, and then I label it. And then negative 2.8 is right here. Even though, sorry, I tried to, I'm going to just do a little arrow here. I didn't divide them up nice and equally, but you guys get the hint. Okay, so I get negative 2.8. So negatives are a little bit different because you want to know which one's greater. If you want to know which one's greater, it's always the one to the right on the decimal line. So since negative 2.5 is to the right of negative 2.8, it's actually greater. So how you remember the greater than or equal to sign, either it choose the greater value, like the Pac-Man is towards the greater value. How I learned it when I was younger, it always points to the lesser value. So since negative 2.8 is less, the symbol points to the lesser value. Either way, it doesn't matter. So negative 3 over 8 and negative 5 over 8, I would not change that to a decimal because you're already in eighths. So you know that it starts at 0. I'm going to go in the negative direction, so I need negative 1. I need to divide this segment into eighth equals. So 1, 2, 3, 4, 5, 6, 7. Gives me 8 equal spots. From 0, I go to negative 3, so I'm going to just change my color. So negative 3 over 8 is here. And then I'm going to go 5. 1, 2, 3, 4, 5. And I'm going to put the label on the bottom so not to confuse. And now negative 3 over 8 is to the right of negative 5, so it's actually the greater value. So I always point to the lesser value. So now what I want you guys to do is try do these class examples using decimals. I'm going to go to my next video and hopefully, because I have to stop because it's getting a little bit too long of a video. So I'll do this class example in my next video.